welcome back to the channel. So there's this prime machine video where the algorithm is 1 billion trillion times faster. Let's watch it.
1.6 million% faster. It's hard to even display visually because it shows up as nothing. Today I'm going to show you the 7 steps taken to improve the running time of an algorithm, but here's the kicker. The slowest one was O of n and the fastest one is still O of n. And along the way, I'm going to use common optimization techniques that you can use in any application. And then we're going to get a little...
Like, this is very interesting. O of n. How is it possible that one is faster even though like it's O of n? It's because, you know, the time, you know, of the operation is probably different. You know, it's, you know, each operation is like probably takes more time. It doesn't take more operations, it just takes more time.
A little bit exotic and go into the bit manipulation world to really speed things up.
Okay.
Then, of course, compiler optimizations and SIMD and everything to go blazingly fast. But first, the problem, of course, right? So the problem is simple. It was from Advent of Code 2022, which is...
Should I read it? Okay, let's just
find
listen.
14 distinct characters in a long string. Once you
Find 14 distinct characters in a long string. Okay, give me a second. So here's my long string, and we're gonna find the 14 characters. So how would you do that? You go one by one until you find the duplicate. There. And then you rewind here, and you go, and you find another duplicate, and then you rewind here, and you go. And you might be asking, why am I rewinding here? Why am I just not continuing from here? Because that's possible that, you know, I rewound here that starting from this string, there might be 14 different characters. Whereas, you know, if you start from here, you're, you know, there's no duplicates in this substring. That's why. Obviously, this is very simple. The question is like, how can you make it faster? And I think because it's O of n, like the algorithm is probably very similar. And he mentioned bitwise manipulation that I guess he's going to use different data structures.
You find 14 distinct characters, you just report the position directly after those. If you're not familiar with Advent of Code, it's kind of like a fun Santa-themed holiday adventure in which you're solving problems to bring Christmas joy. The simplest solution possible would just be to use a hash set, right?
Oh, so there you go. Different solutions. Hash set. It's basically just just call it a set. It's how is that helping? To start putting in characters one by one, and sets are distinctive, big D. So if like you can't add duplicates, so each time you just check the length. So put in Q, put in K, put in F, put in K. But the length is still 3 because K is a like duplicate and sets can't contain duplicates. So that's, I guess, the fourth solution. Okay.
Grab the first 14 characters, throw them all in the hash set, and then check the length of the hash set at the end. If it's 14, we got ourselves a go. If it's...
Oh, okay. It's not exactly what I told you. He said he put them all at once. That's probably slower.
If not, we need to move forward everything and try again. We need to try again. Oh my goodness, look at that. We have found 14 distinct characters. Now all we...
Okay, that's a solution. That's not even a bad solution. I don't think it's a bad solution. It's really clever to utilize a data structure. But then again, if this requires to be really fast, then
we need to do is report that little J right here, that Jth position, and we've solved Advent of Code. So here's the code. Very simple. We simply go over 14 characters at a time, collect it all into a hash set, check the length of 14,
check the length,
boom, we're done. Now, there's a very simple optimization that could be made. And this is the first optimization, which will lead...
Tell me. I'm betting it's just putting them one by one. It's going to be faster because you don't have to do all the 14 operations at once. Because, say, in this case, say at character 4, there was a duplicate. So I spared 10 different operations. So that's at least twice as fast.
This to a 92% faster runtime.
Oh, my bad. Not twice as, it wasn't twice as fast.
And of course, that is to insert characters one at a time. The moment you detect a duplicate, you do not process any further, and we go to the next set of 14. I know it's shocking, right? 92% faster for such a simple if statement. Let's go to the next level of optimization. This is going to improve the running time 8.9-fold, practically an order of magnitude faster.
Okay, let me cheat. What's in here? Fast, simple, faster, vet. Guess that's vector, right? It means vector. But what's a vector? Like, those of you who code JavaScript, you already know what a vector is. In JavaScript, the vector is basically the array. I know, it don't make sense. It sounds stupid, but it's basically that. Because normally in like normal languages like C and Rust and whatever, the array is just the data structure. You don't get the fancy methods to like concatenate and then set if it contains, you know, in JavaScript you get that. So it's a more complex data structure. So I guess he was using vector, and with the vector I guess you get the contains method. So you can quickly check if an element is within the array, which should be basically the same as going through an array, but I guess it's like the same number of operations, but it's probably slower.
Faster, and it's going to surprise you how we do that. That, of course, is to use a vector instead of a hash set. It might be a bit counterintuitive. You're thinking, well, why would checking every position somehow be faster than a hash set lookup? Aren't those constant time? Yes, but so is a single vector lookup. It's also a constant time. But I want you to think about something. When you see big O of 1 constant time, it's kind of a lie.
O of 1 constant time is that getting an element out of array. It's a constant. Getting an element out of the vector is also a constant time. But I think what it tries to say is the time is different.
Of a constant multiplied by 1.
There you go.
Now, what is that constant? When it comes to a hash set, that constant is significantly larger than a vector constant. And that should make sense, right? Because when you're talking about a hash set, you have to compute a hash and an index into a large table. Inside that table, you then have to go to that entry and potentially scan through some couple item list if there are any collisions and check for equality. Whereas with a vector, you're still allocating on the heap like a hash set, but you just simply have to follow a reference and calculate an offset into a memory region. That's just going to be super fast in comparison. And the code's not that much more complex. We create a vector instead of a hash set, and we simply have to call contains instead.
Oh, there you go. Contains. There you go. Contains. That's what I said. It's like you can utilize the function of that vector or array for JavaScript users.
Instead of checking the return value of insert. It's really not that much different, but it is significantly faster. And the same code, but in JavaScript, is 6.7 times faster. It works in both languages because
so he could do that in JavaScript because, you know, you have the array.
Adding and checking a list in general is significantly faster than a hash set on a small scale. Small scale meaning a few items, like 14. All right, the next one should be obvious what we're going to do here, and this one will be 26 times faster.
Array. I bet, okay, there's it on the screen. A static array. What's a static array? You don't know because you code JavaScript. Static array is when you set the size. Probably in some way you can do that in JavaScript, but it's not the same. It's not the same. It's not the same. It's a different array. So it's same, different, but still different. Because this is a classic array. When you don't have the fancy methods to just call contains. Can't. You need to iterate through. You can do it manually, as you can see. He's iterating through it.
Which, of course, is to use an array instead of a vector. It's stack allocated, and we get like some cache locality kind of benefits here. Much, much faster. But like, obviously, this one's a bit more work because
cache locality is when you have the stack. No, this is the stack, and this is the CPU. Okay, and here is your array. And you access one item, and the CPU tries to predict which is gonna be the next one and just caches it. But okay, but I don't know if in this case it's just so small. It's probably everything is in the
Now I
CPU
have to keep
cache.
track of the index as well, because I don't want to keep checking all 14 elements every single time, but just a subset of them. But still, not much more complicated than our previous solution. Now, I know at this point this has all been a bit surprising, especially if you have not used a real language meaning a language that has static arrays. Hey, sorry, JavaScript! What about array buffer?
Sorry. I'm using JavaScript, by the way, and PHP and whatever. Is it none of them has static arrays?
I mean, they kind of do. But real talk, these next couple of optimizations are gonna be a bit wild. We're gonna go from 26x to 233 times faster. We're starting to get into
bitwise,
the blazingly faster category. All right, before we can go blazingly faster, which is technically a word, you first need to hit the subscribe button, and I'm going to explain to you about bits. Because
it's correct. You gotta hit the subscribe button, and the like button, and the Discord button, and the Patreon button. Just hit every button. It's so easy. And also, subscribe to his channel as well.
From here on out, all the solution involves some bit manipulation to gain some super speeds, because we no longer need to use an array. We can use a singular 32-bit number to store the state of our search. One thing.
Oh, of course. Look, you get the what's the I32, U30, whatever. So imagine this thing, it's 32. Position it at 30 position, either 1 or 0 at each single, but you have like 32 of it. That means you can technically use this as an array of ones and zeros. So if I want to put in A, I can set the first bit, so the 0th bit, because this is an array, 0 bit to 1. This is the first bit. If I want to put in B, I just put in 1 again. The rest is 0. And if I want to put in the D, yeah, I would like to. You just change this to 1. And now you have A, B, not the C. They have the D in.
You have to understand about ASCII characters is that there is a numeric value associated for each one of them, and they happen to be contiguous from 97 to 122. Second, a U32 is an unsigned number that has 32 bits. You can think of that as an array that has the ability to store a true or a false in 32 positions. A true being a 1, a false being a 0. That means any character that's moduloed by 32 will result in a number between 0 to 31. Which is how many bits are stored in a U32.
Or you can or you can just you know, don't really need to modulo, or maybe that's for just like subtract 96 or 97.
Example, let's say our search state is 0. We have not seen any characters yet, and we want to insert the character D. D, or 100 modulo 32, is 4. A left shift operator is the equivalent of multiplying by 10. That means we're going to shift this 1 over by 4 positions, thus equaling the binary representation of 10000, or binary 10,000. So
it's not actually like multiplying by 10, like in 10, because this is binary. We're not in decimal system. We're binary, so you're just shifting the bit. It's not like if you were to take this number as a decimal, it's as if you were like multiplying by 10. That's true, but it's bit shifting. You're shifting it 1 position, which in decimal would you know, equal to multiplying by 10. But yeah, I think this is what he meant.
Our state is equal to 0, and we OR it with our new binary value that we just created. The resulting value will be binary 10,000. Let's say our next character is an A. Following this equation, it will yield a value of binary 10. If we OR in binary 10, we will get out the value binary 10,010. But how do we check to see if that binary has already been set before we set it in? Well, we just simply use the logical AND operator. Using our previous example, we would run the AND operator on it, and we'd get out a value of 0. Therefore, these two values do not share any common.
Yeah, so you and the previous, this is the previous array of stuff, and this is the new, this is letter B, and just and if there's zeros, then it's, you know, that's not there. Another way would be using the AND. So you have, what was the example? It was like 1 0 0 0 and okay, and 0 0 1 0, and using the OR. I don't know what the symbol is. So OR it. It's gonna be like that. And if I compare it to the original one, if it's not the same, then this is, you know, this is a new character. So it's the same thing.
And ones. Now, I know that was a very abbreviated version of binary. If you want to learn more about it, I'll throw a link in the description. Go check it out. It's directly below the like button. So here is Benny's algorithm, and it's actually quite clever. So we do the state thing that we talked about earlier, and we grab the first 13 characters in the sequence. And here's the secret sauce. It uses an XOR. And XOR, think of it like a toggle. If there is a 0 in that bit position, it will flip it to a 1. If there's a 1 in that bit position, it will flip it to a 0. Exclusive OR, or XOR. So we do the same operations that I showed earlier, except for using XOR. That means we have toggled on 13 characters at this point. From here, we just go over the input 14 at a time. If you're not familiar with the Windows operation, it literally goes from 0 to 13, 1 to 14, 2 to 15. It just does a nice window for you. And the position iterator will return the index of the first true result. Meaning when I return true right here, it will return the index, not the value that happened at. All right, so we grab the first and last character in our window. Now remember, our state has the first 13 characters. We toggle on the 14th character, so now we have a possibility of having 14 ones within our state. If we do have 14 ones, then we have found the position we're looking for. Then we remove the first character that we saw. That means we go from 14 toggles down to 13 toggles, from 1 to 13. Then we do the loop again, adding in the next last item in the window, which is now the 14th position. So now we have from 1 to 14. We do the distinct count again, then we remove the first and go to the second. And we keep doing that little window crawl motion over. This clever algorithm earned Benny 233 times faster than the hash set, or 23,000% faster. It is incredibly clever algorithm. Hats off to Benny. Damn it, Benny. What a smart man. And to think my solution was only like 100x faster than the hash set one.
Look. Oh, it did the thing. You just compare it. Okay.
I feel so stupid looking at Benny's super clever window crawling solution.
That's great.
Let's kind of get into our final form here. We're going to look at the algorithm that sped up Benny's by over 4-fold. It was approximately 1,000x faster. So instead of walking through the idea, let's just walk through the code on this last one because it's just mind-blowing. So the first thing we do is just start by going through a fixed size windowing right here. You'll notice that we do a input get from index to index plus 14. So that is a constant size window. It's very important to remember that. Next, we create a state variable, 32 bits, just like Benny's solution. Next, we're going to go through that slice, and we're going to iterate in reverse. Now, for me personally, when I saw this, that means we had to take an iterator, get all of the elements, collect them all up, and then walk backwards through them. I thought there's no way this is faster than Benny's. We do the same operation. We take the modulo 32 of the bit. We test to see, is that bit already set to 1? If it is set to 1, then we found a place of a duplicate. We then shift on that bit using the OR operator. Then we return whether or not we've seen this byte already. So here's one of the two mind-blowing optimizations. If we have seen this byte, since we're going backwards through the list, we can actually jump all the way to this position plus 1. That is a huge optimization. We're going to cut.
So you go backwards. I'm going backwards and try to find a duplicate. And it's okay. Okay. Where? Okay, there was no K, there was no Y. F. If I was to start from the beginning, I would continue from here, from the F. But because I started backwards, I can continue from K, and I gained 1 position. It kind of don't make sense, but it makes sense. And maybe I'm just too dumb, but it kind of makes sense because backwards means that you potentially can gain a position, definitely not lose one. There's no way. Worst case scenario, you find the same position. Oh my god, what a genius.
We don't have to look over and over again for. If we do not find a repeat character or the false condition, we actually return this index, which is correct. This is the position of the 14 contiguous characters. Now you're probably asking yourself, how? Show me how this was so fast, because I don't understand why going backwards through a list was faster other than that little jump. But you still had to iterate over everything, right? Right?
Yeah, but that jump was, you know, you potentially gain a bigger jump. So
check this out. This is the Compiler Explorer. This is godbolt.org. So first I put in Benny's solution right here so we can look at it first. Now, the first thing that you'll notice is that the input right here, since it was a fixed size, what did the compiler do over here during optimization? It actually unrolled the loop. It just made it all in line. So there's no jumping back and doing this a whole bunch and then jumping out at the end. Then we get to this, our Windows 14. Now this is kind of interesting because this is pretty much the primary loop right here. We just go over this code over and over and over again.
To my eye, it seems like faster, but it doesn't mean anything. So there's the loop, there's jump if not equals, goes back here.
It's pretty fast, right? But now let's look at David's solution. So we have the same thing happens to David's solution right here.
What's that all this stuff? I never seen anything like this before. What's that? VPMO, whatever.
It actually gets unwound. So that reverse iterator happens in reverse right here. You can see it right there. Look at that. 11, 10, 9, 8, 7, 5, 3, 2, 1, and then whatever this means. I don't even know what it means. And I have been told that what's happening up here is all the SIMD stuff that's happening. That means single instruction is multiple data calculations in a single go with the compiler. That means you can massively speed up what you're doing. So not only...
Okay, unfortunately, I don't know what that means, but it means speed. It's speed.
But you're probably asking yourself, wait. That one was 16,000 times faster?
No.
That was just shy of 3 orders of magnitude faster. 1,000x faster is 900.
So there's a better solution? How? What did you do? What did you buy? What? How? It probably has to be something with a bit something really clever.
183x faster. So how did we make it that much more faster? Of course, I just used my 64 threads that are just doing nothing. Come on, of course.
Oh, so you cheated. You cheated.
I'm gonna do that, and that allowed us to go blazingly fast. In fact, 16,000 times faster than the original solution. I know someone's probably like, well, that's kind of cheating, isn't it? I mean, it's a little cheating. I mean,
it's cheating. What are you saying? It's cheating.
Part of an algorithm, right? We're just improving upon the algorithm. It's a very simple set of work to parallelize. In fact, it's so fast that Google Charts, I can't even get a blue line to show up here. That's how much faster it is. It is so fast that the original solution would process 3.84 megabytes of data per second, whereas the multi-threaded final solution did 617 gigabytes per second. Of course, it only did it for about 11.9 milliseconds because that's all it took to cover about 800 megabytes worth of data. Of course, the 983 times faster solution is brought to you by David A. Perez. Go give him a follow on GitHub. Now that's blazingly fast. I hope you enjoyed this. Hey, hit the like button. Let me know down below. It was a lot of fun to do this. This was all obviously done on Twitch. We went through all the optimizations and everything. Mwah. Glorious times on there. Thank you for watching. The name is the Primogen.
What a great video. What a great video. I love it. Don't forget to subscribe to the Prime. And don't forget to subscribe to me as well and like the video. And join Discord, join Patreon if you want to. And so thank you very much for watching. See you in the next one.